maybe. Yeah, I just thought you.
No, yeah, I just looked at it and I never got that question. I put like a 9 instead of a 3. I don't know.
All right, so guys, today we're going to learn, or this chapter we're going to learn about a new way to graph. Okay, so far when we've been graphing, we've been doing everything on what we call a Cartesian plane. Cartesian plane was named after Descartes, hence the Cartesian. And you know about Descartes' rule and a couple other things that he did, but he was a brilliant mathematician, philosopher. He did all kinds of different stuff back in the day. But he graphed everything based on X's and Y's. Okay? Well, there's another kind of graphing system or system where we can operate on, and it is called a polar graph. And a polar graph is how actually our latitudinal or longitudinal lines are set up. So, like for instance, if you look at, I think I have a little chart. If you look at our globe from the north, we have the North Pole, and the North Pole, hold on. Come on. There we go. Okay. So right here, slowest computer ever. It is new. I have no idea why it's this slow. Like, look at it. Okay. Does that look? Okay, it looks a little fat to me. So anyway, I'll pull it down. That look more circular. Okay. So this is what our north and south pole look like from when you basically look at it, the globe from the north. Okay, and it's measured. All of these lines right here are our longitudinal lines, and they go 0 all the way through 360 if you're looking from the top. Okay, so now granted, I don't know if they go 0, 15, 30 this way or 0, 15, 30 this way, depending on the north and the south. Honestly, I don't know. But our pole will operate on will look like this. And then these rings here would be the latitudinal lines. And you know, like if you remember geography or whatever it is, or whenever you learn that, I don't know. But the rings right there usually they go from like 0 to 90 degrees, and they're measured, like if you're looking from the top of a globe right here, it's measured like, right, you kind of basically go down to the equator and go up 10, 20, 30, 40, all the way up to 90 degrees. Okay, well, these rings on a polar graph, when we're operating on them, the degrees part from 0 to 360, that part's the same. But the rings, or unless I want to use radians, the rings represent units away from here, which really, if you think about it, makes a little bit more sense. I mean, if I wanted to get, I mean, granted, with the aisles here and stuff, if I want to get from back to Catherine's, walk that way. That's what X's and Y's do. It's almost like a military-esque like movement. But polar graph just says, if I want to get from a place to a place, I just point in that direction a certain degree and walk that way. Yeah. I am. Got a new system, man.
You never even knew it.
Nice. Finally got it wired up. By the way, if you're not here, if I told you this, I'm live all day long. So you can just hop on that Google Meet, that same one we've been using all year, the hurry_meet_2020. And you can hop on that. For instance, yeah, you can wave, everybody. Well, they can't see you. They're feeling your presence right now. But they just come on live now, so I really don't have to record anything. Our virtual people. We've got Pascal, Yvonne, and Sid. Everybody's clapping for you. Yeah, so we're live all day long. So if you're ever sick, just hop on. You can hop on this period. And honestly, I keep it running all the way through the end of the day. So if you want to sleep in, if you're sick or whatever, I understand, you could hop on during the 7th period, hour 2. And I'm still recording it. So you probably could just pick it up whenever I get it uploaded, which normally is sometime. It takes a while for Google to process the meet and then send me the link. And then I got to do some downloading up to my YouTube channel. which you're welcome to subscribe to.
Oh,
My numbers are really getting up there. But anyway, so here, but thank you for the reminder. But this is a polar graph system. So what we're going to do is first we're going to talk today just about how to go from a coordinate, an X and Y coordinate, to a polar coordinate. Because I could, if I wanted to, lay a Y and an X axis over the top of this. And I could say, okay, what does a over 4 up 3 point, granted 4, 3 is what it would be on an XY plane, what would it look like on a polar graph? So a polar graph doesn't use X's and Y's. There is no X axis. There is no Y axis. There are angles, and we use R, it's almost like a radius, but there's a length from what we call the pole. So this point right here, we call this the pole, and that's 0 degrees. So we measure everything from 0. So for instance, if I had something like 6, 30 degrees, that would be in polar form. That tells me to go 6 units towards 30 degrees. So I would point myself towards 30 degrees, and I would go out 1, 2, 3, 4, 5, 6, and that would be this point. Now, unlike rectangular coordinates, that's polar, rectangular is me using X's and Y's. Polar, R's, and thetas. So the R is the distance you move, the theta is the angle that you move. Unlike these, where there's only one coordinate that matches, there are lots of coordinates that could match this. For example, I could say 6, 390 degrees. I still end up in the same place, don't I? Because I'm going around 360 and 30 more, still out 6. You with me? So there's an infinite number that I could do by just adding and subtracting 360. But also, I could do this thing. You see what I'm doing there? Here, I am literally pointing myself towards 210. Think about it if I was walking. Instead of pointing myself at 30 degrees and walking 6 steps, I'm pointing myself at 210 and doing what? Walking backwards 6 steps. But I still get to the same place. So if I were to ever give you a coordinate that's polar and say, hey, give me some other coordinates that would put you in the same spot, or equivalent coordinates, you got 2 options. One, you could just do what to the angle? Add or subtract 360. Or you could do what? Add 180 and negate the direction you're moving. Are you with me? Because adding 180 is changing direction, but so is the negative, changing the direction. So it's like a double negative kind of. And at that point, now I could add a bunch of 360s or subtract 360s to this. Are y'all seeing that? So those would all be the same thing, but rectangular wise, there would only be one. Now what you're going to have to be able to do, no question? Oh, what you're going to have to be able to do is convert. So could you take a polar coordinate right there and change it into an XY coordinate? Now, you know the math to do it. You just have to think for a second. And then once you understand the thinking, you have to know that don't take the time doing it that I'm about to take right now. Just make sure you have that process down pretty quickly. You're just wasting time. So think about the picture. I went 30-degree angle. So that's 30 from here. I did a 30-degree angle. And then I marched 6 in that direction. And what I want as a rectangular or a Cartesian coordinate, I want to know what the X and the Y would be. Well, if I want to know the X, I basically want to know that length, don't I? And if I want the Y, I want that length. That would give me X, Y. Well, what do I need to be able to do that? Just a little trig, right? Now, that's a special angle, special triangle, so you don't really need trig if you memorize your 1, 2, root 3 rules. Are you with me? You could have done that. Well, then it's always the ratio 1, 2, root 3. So you could have gotten away with it just with proportions, but that's not always going to be the case. You're not always going to have a nice unit circle angle. So what I do is think in terms of trig. So right here, what relationship includes y 6 and 30 or x 6 and 30 that would enable you to solve for x and y? Start with the x first. What could you do to solve for x if you didn't know that special triangle? Like say the angle was 27 or something like that. Okay, you could, but is there an easier way? Like it's because it's a right angle right there. I really don't need, but you could, yes. But it would simplify down to what? The cosine formula, right? What's cosine of 30? That's cosine of 30 is just what? X over 6. So what does x end up giving me? 6 cosine 30. So if I want the x value, all I got to do is take that 6, cosine that, and whatever it spits out is my x value, which you know in this case would be what? What's the cosine at 30 from your unit circle? Square root of 3 over 2. What's square root of 3 over 2 times that 6? 3. Now, I'm not going to pull out my cosine formula. Guys, hey, I'm not going to pull out the cosine formula every time. I know from the unit circle, what do x's relate with? Cosines. What do y's relate with? Sines. Why do you think x is always cosine of the angle on the unit circle? Because the value there was 1. I didn't have to put anything in front. But now the value is 6. We're 6 out. The unit circle is right here. So now instead of going cosine sine for xy, I'm just going to go 6 cosine 6 sine. Because finding the sine of 30 is y over 6, and by the same process, my y is going to be 6 sine 30. So why not just remember, hey, it's just like the unit circle. On the unit circle, every coordinate, x and y are represented by cosine angle, sine of angle. The only difference is you're putting like a magnitude out in front. You're putting in a length out in front because you're stretching that length out by a length of 6. And then you know that 6 sine of 30 ends up being 6 times a half. And those would be the rectangular coordinates. And if you didn't know that for sure, if you didn't know how to graph that, remember root 3 is about what? 1.7-ish? So what's 3 times 1.7? 5.1-ish maybe? So over 5.1 up 3. 1, 2, 3, 4, 5.1. So actually a little bit closer probably. And then up. And it's hard to see up 3 right here. But whatever that length is, if that's 1, you'd be going up 1, 2, 3. Are you with me? So it might be easier to look at it from right here, 1, 2, 3, and then just bring over a horizontal. Say, okay, if that's 3, 4, if that's up there vertically, just kind of eyeball that over, and that's what I'd be looking at. Y'all seeing this? Yes, no? So that's converting from polar to rectangular. Know this process. Now, what if I give you rectangular? Like, what if I say, all right, now you've got a rectangular point, and I want to go from rectangular to polar. So what if I gave you, say, -2, 7? So -2 would be left 2. That part's the same. 1, 2, 3, 4, 5, 6, 7 is up here somewhere. I guess I could eyeball it. And just eyeballing that puts me somewhere, maybe right there. So that's pretty close to -2, 7. Y'all with me? But I don't want the rectangular now. I want the polar. So I want to know, okay, how far out were we? And what was the angle? What was my angle? I want to know the r and the theta. Anybody got any ideas? If I know x, y, how to find r, theta?
Use the inverse.
Okay. I know x and y. So if you think, hold on that thought for a second. So basically, this is what I know. I know that's right angle, that's a -2, that's a 7. I want the r, and I want the angle right here, which is kind of going to be like a reference angle idea, but it's going to be even easier than that. If you know x and y, what's the easiest way to find the hypotenuse? Okay, so to Pythagorean theorem, x squared plus y squared is r squared. That's not going to be a big deal, is it? So I know the x is -2. I know the y is 7. I can get r equals 4 plus 49 is root 53, which you know is about what? You had to graph it. 7-ish. 1, 2, 3, 4, 5, 6, 7-ish. So that's about right. But what else do I need? The angle. Now, I heard somebody say inverse sine, inverse tangent. Well, now that I have the r value, now that I have it, I can totally find the angle because I have all three sides. So I could use inverse sine or inverse cosine or whatever, inverse tangent on all, because I have all three sides. But if I've made a mistake, that r is going to mess up my inverse cosine, inverse sine. But what uses x and y? Inverse tangent. So why don't we go with inverse tangent? But here's one thing you got to be careful about with inverse tangent. So remember, because tangent theta, this is because tangent of theta is y over x, I can find my angle by doing the inverse tan of the y over the x. So I'm just going to come in here, but tell me why I'm wrong here. Inverse tan of the y, the 7, over the x, the -2, and look what my calculator spits out. And now I want you to tell me why this is messed up. So, what's my mode? I want to go ahead and put it in degrees. So inverse tan of 7 divided by -2, and it spits out -74.
You have to add 180
Why?
because you're in the quadrant with a -x.
Are y'all with me on that? What do you, good. She said, I have to add 180 because if my point has a -x value, I'm heading over to either the second or the third quadrant, right? And you know that when you use inverse tangent is defined between what? -90 and 90, right? Which means you're forced down here into the fourth or the first quadrant. So if you ever have an angle that you're trying to find that's not in the first or the fourth, your calculator is going to lie to you. And you know this is not in the first or the fourth because your x was negative. So what do you do to fix that? You just add a 180. And when you add a 180, it fixes it and sends it, what, 105.8? And when you look at this, 105.8, that's 105, that's 120. That was a little bit bigger than the 105. So, root 53, 105.8 degrees. Are y'all with me? Okay, so that is how to convert one point to another. Now what you're going to have to learn how to do is convert equations from rectangular form, which are like functions, conics, all kinds of stuff with x's and y's, into r's and thetas. So if you understand the point thing, because that's really just trig, let's think of the other thing, how to convert an entire equation. Basically, like how to take something like x squared plus y squared equals 25. How do I turn that into an equation that doesn't have x and y anymore, but just has r's and thetas? So what I want you to do is think, right now, what do you know? Like, what are the things that I have written down so far that you have used to convert? I've written down some statements, and you've used them. What are they? How do we find x? What did we do when we wanted an x? R cosine theta? So, if I have an x in my problem, and I want to get rid of it and replace it with something that does not have an x, but just has r's and thetas, that looks pretty good. So I could take this, put it over here, and go r cosine theta squared. What did we do with y? And notice it doesn't have x in it anymore. It just has r's and thetas, which is changing it to another way to graph these. What about the y? What was that equal to? R sine theta? So I could come over here and say r sine theta quantity squared. And right there, I have just changed this from a rectangular to a polar. And to show you how this makes sense, let me ask you a question. What if I were to give you this right now and say graph r equals 5? In your mind, what is that saying? Like if this is all you have, and I say graph it, it seems to me like it would be a circle because it says nothing about what the angle can be. So if it doesn't have anything about the angle, it just says, as long as your r is 5, I guess you got to mark it. So from here, you could go 5 that way, 5, 1, 2, 3, 4, 5 that way, that way, that way, that way. You could go 5 in any direction, right? And if you can go 5 in any direction from the pole, that gives you a circle. That's what this is. It's just not cleaned up yet. Take a look. If I square this, don't I get r squared cosine squared plus r squared sine squared? What if I factor out the r squared? Don't I get this? What do you remember about sine squared plus cosine squared? It equals 1. So now I'm down to r squared equals 25, and if I square it both sides, I can get r equals plus or minus 5. And what does minus 5 mean? Just go the other way. So instead of going 5 that way, I go 5 that way. Is that really any different? So you can see it's still the same thing, but it's graphing it a different way. This depends on you moving over an x and up a y and making sure that those two movements, when you square them, add to 25. Whether it's over 3 up 4, over 5 up 0, over 0 up 5. All of those will make that true, but this just says, hey, go out 5 in any direction because I didn't say anything about your theta. Are y'all with me on that? Now, are we going to be simplifying all these all the time? No. We're not going to be doing a whole lot of that anyway. We're going to be doing a little bit of going from rectangular to polar. And you'll notice there's actually a totally different way to graph on your calculator. I really, honestly, the Inspire I don't think is as great as the 84. I like the 84 a little bit better. But check this out. Okay, I'm pulling up your Inspire. I'm going to zoom in a little bit. Okay, so you normally, if you're on graph, I'm going to go to graph and I'm going to delete it all out. And there is a way to actually do a little bit better graph on this, but you're going to have to just roll with this right now. If I go to tab, like I'm normally about to do a function, you see f1 of x, don't you? Well, if you want to graph in polar mode, you have to change that. So I'm going to hit escape, and I'm going to actually go to my window. I'm going to go menu, window, and hit standard just so it looks a little bit better. Centers it at the origin. Now, watch what you do now to actually graph or type in a polar equation. Go to menu, and instead of choosing, for graph entry number 3, this is saying what kind of graph do you want to enter? If I choose 3, we are normally on function mode. There's actually a relation mode too that actually allows you to graph conic sections because those aren't functions. And you can actually type in stuff like x squared plus y squared equals 25. It doesn't have to be y equals. But right here, look, polar mode. So if I hit 5 on polar mode, 5, you'll notice now it doesn't give me y equals, it gives me r equals. So I can graph things r equals, but it also gives me a domain. It says, hey, this one's going to only graph the angles between 0 and 6.28, which is like 0 and 360 degrees. So if I did r equals 5, it's going to graph, which I just had right here, r equals 5 and hit enter. It's going to go 5, and it's going to start here and go all the way around to 360. Now I know on an Inspire, because it's so fast, it just went boom, and you saw the graph. But look at the 84. On the 84, which is antiquated technology.
Mine was just like a little.
I mean, it didn't work. Oh, are you in radians?
No.
Put it in radians. Sorry. You gotta make sure you're in radians. Now check this out. If I had a TI-84 I go to this and wait a minute, window. And I don't use this much anymore, I forget. Mode. Okay, right here. I'm gonna go to polar. Zoom 6. Okay, check this out. If I go to R equals 5 here, watch the graph. Because it's slower, you can see what it's doing. It literally is starting you know how, again, you don't see this, but on the 84s, if I'm graphing a line, I see the line curve from the left and it graphs it out to the right. Because it's literally starting at your negative values and going through your positive values. We had ours defined from 0 to 360. So when I hit graph on this, you're going to see starting at 0 out 5, and you're going to see it make a circle. It's literally going through all the degrees. That's how it's graphing this. And it doesn't look like a line because my window's not square, but it does now.
Wow.
Are y'all seeing that? But you can see that it actually rotating through the 360 degrees. So the weakness of this calculator to me is actually a strength because you can actually see what's happening. And look, if I wanted to change that, I could change it and make it go twice. Like if I go to window and go, oh, my min and my max is not 0 and 360 anymore. If I wanted to go 0 to 720, okay? And let me show you something. If I did that, I can actually check this out. All right, check this out. I'm putting a little dot so you can see the dot move. Nope, you can't. Oh, I didn't hit enter on it, I don't think. Okay, check it out now. You can see it, 0 to 360, another 360. But because it's going through those values that you're seeing. And there's all kinds of graphs that we can do on this that actually are kind of interesting when I start doing weird stuff like and just start playing around with steps. That's not weird. What could make this weird? I'll tell you what, we'll do it tomorrow. I'll come up with some weird ones and I'll show you because that's not exciting. How about this? That was kind of interesting. Did y'all see that?
Whoa. It was like one of those.
Like right here?
Drawing. Whoa.
So you can actually start doing some interesting things with this.
Wow.
Ah, fun. Okay. But anyway, hey, real quickly, we got 5 minutes, right? Now, what would you do if I asked you to go the other way? Like, what would you do if I gave you something like this? Okay, by the way, remember, X, R cosine theta, Y, R sine theta. That's all you need right here to be able to go from rectangular to polar. And then you can solve for R if you want. Now, you also used this, right? And you also used this when you went the other way. So what could you do if I started you out with something like R equals 3 sine theta, and I want you now to go to rectangular? Like right now, I'm guessing you don't have any idea what that looks like. But what if I wanted to know what it looks like? So I want to change it out of this form to a rectangular form because I know a whole lot about rectangular forms. Maybe they're lines, maybe they're quadratics, maybe they're conics. So how can I go backwards? How can I get rid of a sine theta using this step? What is sine theta equal to? Is it y? Or is it y over r? Okay, so my first thing I'm going to ask you to do is replace your sine thetas, your cosine thetas, your tangent thetas. Replace those with your trig rules. Do that. So the first thing I'm going to do is replace that with y over r. All right, so first thing, get rid of your sines, your cosines of theta. Get rid of those. Replace them with what you already know about trig. Second thing is, we don't ever want to look at fractions. So if I see a fraction, immediately clean it up. So right here, I've just made a fraction. So what could I do to immediately clean that up? Multiply both sides by an r. That gets me to here. Now, I'm fine with the y being in there. That's my goal. But I don't want thetas and I don't want r's. I still have r's in there. What can I do to get rid of r? Yeah, if r squared is x squared plus y squared, then I could replace that with x squared plus y squared. Have I now gotten rid of all of my r's and thetas? Does anybody have a guess on what that is? It's a circle. Now, I don't know exactly what kind or how big it is yet, but if I move that over to this side, isn't it just ready to have the square completed? Right? Half of that squared is 9/4. Add a 9/4 over here, and I get x squared plus y minus 3/2 squared equals 9/4. And you can see I have a center with a radius there. And no, I'm not going to make this about a conic sections test, but this ended up being an equation of a circle. Are y'all seeing that? Okay, what if I gave you something like this? R equals 6 cosecant theta. Now, I already told you once, the first thing I want you to do is replace that. Okay? So, get rid of the trig angle stuff. So what is cosecant of theta? If sine is y over r, right? Then what is cosecant? R over y? And what did I also say that I didn't like? I didn't like fractions, so multiply both sides by a y. Now, is there anything you see that you could do right here?
Take out that r.
You can divide both sides by an r, and what do you have?
Y equals 6.
Y equals 6, so that's a horizontal line. So you're telling me if I graphed that, I would actually have a horizontal line? Let's see.
I bet so.
If I graph 6 cosecant theta, I'm going to have to go divide it by, because I'm using a different calculator. Oops. 6 from 0, 360. Horizontal line.
Wow.
But I never would have known that here, would I? All right. Hey, see what you can do on the homework. Use these principles. If you run into trouble, let me know. Y'all have a good one.
Can you do my